Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on metallic bonding. Previously, we discussed the general properties of covalent compounds. We learned that this type of compound is most often a liquid or a gas at normal temperature, although they are sometimes found in the solid state. We learned that covalent compounds consist of molecules and therefore do not conduct electric current when molten or in aqueous solution. Through some experiments that we discussed, we learned that these compounds also have low melting and boiling points and are insoluble in polar solvents. They are only soluble in non-polar solvents. In today's lesson, we will explain the formation of metallic bonds. We will discuss the electrical and thermal conductivity of metals in relation to metallic bonding. We will also look at some examples so that the concepts are easier to understand. Students, if we look at the highest energy orbitals of metals, we find that they are occupied by a small number of electrons. Let us look at an example. If we look at the S-block metals, such as sodium and magnesium, we can see that only 1 or 2 valence electrons occupy the s orbitals in the outermost levels. If we look at p-block metals, such as thallium, lead, and bismuth, the p orbitals of their outermost levels are also only partially occupied. The d-block metals contain partially filled N1d levels in their atomic state, or principal oxidation states. Compared to the bonding in other types of crystals, the bonding in metals is quite different. The valence electrons of metals are not held by individual atoms, as they are in some elements. The electrons of metals are delocalized and mobile. In other words, the valence electrons of metal atoms are free and able to move throughout the structure. As you see here, the valence electrons occupy space all around the metal ions. The metal ions are organized as a crystal. Metals are a matrix of positively charged ions in a sea of delocalized electrons. Metallic bonding occurs as a result of the attractive forces between the metal ions and the electrons that surround them. This image shows a sodium metal crystal. It is an organized array of sodium plus ions, surrounded by a sea of mobile bonding valence electrons. The freely moving electrons within metals are the reason that metals are electrically conductive. If we were to pour 100 marbles into a glass jar, the marbles would eventually settle into an organized structure. This is similar to the structure of metal atoms. The marbles represent the nuclei of the atoms, and the empty space between them represents a cloud of free-moving electrons. In a moment, you will see several sentences appear on the screen, one at a time. Read each sentence carefully and determine whether it is true or false with regards to metallic bonding.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. Were you able to determine which sentences were true and which were false? Let us look at them now. Sentence A is false. The valence electrons of metal atoms are delocalized and mobile. Sentence B is true. The highest energy orbitals of metals are occupied by a small number of electrons. Sentence C is false. Metals are a matrix of positively charged ions in a sea of delocalized electrons. Sentence D is true. Compared to the bonding in other types of crystals, the bonding in metals is quite different. Did you answer all of those correctly? If you did, then you are doing great. Students, let us move on with our lesson and discuss the properties of metallic bonding. Not only are freely moving electrons responsible for the electrical conductivity of metals, but they are also responsible for their thermal conductivity, malleability, and ductility as well. Malleability allows a substance, such as metal, to be reshaped. If you have ever visited a goldsmith, you will know exactly what I mean. Gold is an especially soft and malleable metal. This is why goldsmiths are easily able to shape it, along with many other different types of metal, into jewelry of all shapes and sizes. Ductility allows a substance to be drawn or pulled into long pieces, such as wires. Metals are both malleable and ductile because in a solid structure, their bonding is the same in every direction. When an amount of force is placed on a metal, its cations will be forced to change positions while the crystal structure remains intact. When metal is hammered, bent, or pulled in order to alter its shape, the cations simply shift. The force that is applied moves the cations around. They shift around corners of the crystal lattice. Students, we have time for one last activity. Define malleability and ductility. Then, explain why metals are both malleable and ductile. Try your best, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I am sure you had no trouble with this activity. Malleability allows a substance, such as metal, to be bent and reshaped. The ductility of a substance is what allows it to be drawn or pulled out into long, thin pieces, such as wires. Metals are both malleable and ductile because metallic bonding is the same in all directions throughout a metal solid. When force is applied to a metal, it bends and reshapes while retaining its crystal lattice structure. The cations simply move around and shift. In today's lesson, we talked about the formation of metallic bonds. We also learned that metals are electrically conductive, thermally conductive, malleable, and ductile because of their freely moving electrons. This brings us to the end of our lesson. Until next time, thank you, teacher. Thank you, students.